That's great to see you all here. We'll be talking about pattern matching in C# today. In case somebody has a different idea of the agenda, then this would be the time to notice it. My name is Oliver Sturm, Ollie, people call me. Nothing very important on here. I've been working with C# for a very long time. That's maybe relevant to this particular talk, all the way back to when it wasn't even called C#. You guys remember what it was called before, like a working title that Microsoft had? No? Yeah? It was called Cool. I like that. I thought they should have stuck with it. But, I mean, when it first came out, everybody was like, what's with the C#, right? So it's not like they got that right. So anyway, well, so today we're going to be talking about pattern matching. And I will begin at the beginning in case you say I have never really used pattern matching at all. We won't be spending too much time with it, but I'd like to give you a quick introduction overview of whatever all the features were, because there are a lot of features that came into the C# language all the way back to version 7 for the purpose of pattern matching. So I'd like to kind of level the playing field a bit before we get into the more difficult stuff. There are some sort of interesting use cases, and that's kind of a category, if you like, because Microsoft, when they talk about pattern matching, they typically focus on business data use cases, right? So they have some objects they'd like to, for you to write slightly more compact if expressions maybe, or something along these lines, right? And maybe a little more than that, but that's basically what Microsoft primarily focuses on when you look at their documentation or whatever. It doesn't really go very much further than that. Whereas I come to pattern matching from the perspective of a user of functional programming languages, where it is frequently used for much more advanced use cases, and also with a generally different mindset, right? So that's kind of the perspective that I applied there. So that's some of what I'm going to show you. So we kind of move gradually into that. When it says here, interesting cases, we're sort of halfway there. We're going to look at some bits that are not immediately intuitive, perhaps, that go a little bit beyond what Microsoft typically focuses on. And then we're going to see what else we can do with pattern matching that, well, I'm not going to say Microsoft doesn't even know about, because that would be nonsense. They have clever people who were involved with this too, but that they don't really tell you about. That's definitely true. When I first started preparing this talk, which is actually some years ago already, I found that the documentation doesn't even cover various scenarios that I had to kind of figure out with some trial and error to see what the system could actually do. So that was quite interesting. And I'll show you some examples of porting algorithms. Now, this is one of those major concerns, really, that I was trying to address here. I once wrote a book about functional programming in C#. This happened around 2010 or so, a long time ago. And there wasn't any significant pattern matching back then, right? It was based on C# version 3 originally, and some stuff that came a little bit later. And so I was then porting some algorithms from functional languages to C# to try to see how I could do this, how I could reuse these functional approaches in C#. And I found it to be difficult, and I found it to be verbose, right? So some of my implementations ended up taking pages of code, where in a functional language it might have just been a few lines. And so I revisited some of those examples that I implemented back then when I found that pattern matching in C# had been significantly improved a few years later. And that's the kind of mindset that I applied, right? So what if I have algorithms that exist in languages that I don't use or can't use or whatever, right? Everybody doesn't want to go the F# path. And maybe there are existing implementations like some of those that I'm using that were made in Haskell or ML, to throw out a few other functional languages. I was using a book, for example, about functional data types at the time and trying to re-implement them in C#. And that's where the actual advantage that I'm partly interested in this talk here comes to pass, which is that I can then, if the syntax in C# is similar enough to the original, the port becomes a lot easier. and it becomes a lot easier to maintain, even if I don't entirely understand what the original code does in the first place, right? Because that was my problem back then, right? This clever bloke wrote some crazy data types in Haskell. I didn't exactly understand how they worked, and I didn't really care either. I wanted to use them, right? But how do you do that? And then maybe if your port is complicated and you end up making a mistake somewhere, you have no idea how to find it, right? So that's difficult. On the other hand, if I can port in a syntax that is similar enough, then that becomes a lot easier. And so that's the kind of idea that I had in mind when I tried to follow what C# could do by now. So that's where we're going to end up. I have a pretty crazy example to finish us off with eventually that you can totally take back and scare your colleagues with. It's probably not the sort of thing you want to be doing every day, but it's very interesting to see how far C# has actually come with these pattern matching syntax variations that were introduced over time. As I said, for quite a long time, since C#7, we started in with this is thing where we could do simple type comparisons. That was actually a big thing at the time. I don't know how many of you were using C# then, but prior to that, there were always these discussions over should you cast first? Should you first check with is and then maybe use the as operator, or is it better to just cast in parens or whatever? You know, people were back and forth over that. And it was always syntactically verbose if you were going to check for null and then also cast and check the type and whatever. And with this operator, that all went away. And that's why it was very popular back then, but not because anybody really knew that Microsoft was going to use this as the basis of their new pattern implementations that we're following, right? But so basically the simple type check is the simplest type of pattern that we still support today. And that is also very useful, of course, but that's when it all began. In C#8, we had lots of other expression types. I'm going to show you a couple quick examples in a moment. In 9, we had new operators, these logical and relational operators and that sort of thing, with and or not, and also smaller, greater, and similar kinds of comparisons. 10 was only a syntactic improvement, basically, and in 11, however, we got the matching for list patterns, which is quite important for the particular purpose here, because a lot of algorithmic implementations in functional languages use pattern matching on lists all the time, and that was not supported before C#11 came along. So that's kind of the history so far. I asked Mads Torgersen once when I met him, if they intended to implement some more things, and he said, yes, there were numerous ideas that people were throwing out, so we might not be at the end of it yet. But currently, for a little while, new C# features have not actually brought new pattern matching features. We'll see. Maybe there's more to come at some point. Okay, so let's have a quick peek, I suppose, at what that looks like I said, just to bring us all up to speed here. So in C#7, like I just said, this is what we all know, right? We can simply check whether a particular type is represented by a variable, and that's also possible in the case statement up here, which up to C#7 was actually still a statement, right? Imperative. In C#8, a lot of other things happened, and amongst other things, we were now able to use a switch statement as an expression. That is kind of related to pattern matching because you need that in order to use patterns, more usefully to compute expressions and so on. And now all of a sudden it was in fact an expression. We also had this default value here, the underscore thing, that did not exist in the same way prior to that. So a lot of these kinds of things came in, and then we introduced new patterns too, like this one here is a property pattern. So we're checking that the DT, the datetime value, has a property of a certain value and so on, right? I'm going to go through these quite quickly. This is basically syntax stuff that I'm sure a lot of you are familiar with. We also had the tuple pattern is what it was called at the time, right? So we can take apart a tuple into its 2 bits in this particular case. Microsoft now refers to it as the positional pattern because it has since been extended to also take care of deconstructors, not just tuples, right? So, but back in the time frame here, it was called tuple pattern because it only worked with those. And we were also able, let me just break around this one here a bit, to map nested objects like this here, so they can match properties on multiple levels at the same time, right? So a lot of this kind of new stuff came in. Microsoft has a lot of examples about using business objects with these kinds of patterns and so on. Interesting one down here, prize question. I hear that the Microsoft team was a little bit surprised when they saw that users were making up this pattern right there. So for example, customer.address is, and then there's just, you know, two curly braces followed by a variable name, A, right? What could be the point is what they were wondering, so I hear. So there are several points. This basically tests that we're working with an object and that it is not null, right? So that's what the test does. Now, of course, we actually have a special pattern for that. So we could also say, if customer.address is not null, that is actually a supported pattern, right? So that would be a little more expressive if you really wanted to test for null, and that's what you care about, right? That's the only thing you care about. So the interesting thing is that some people use this in order to implement a type of with statement, because you see that now, the variable A here can now be used down in this expression, for example, to reference the longer item at the top, customer.address, right? So if I sometimes have some kinds of nested object structures and my path is this long and I have the need for some reason to repeat it multiple times in my code, then I can use this expression right there to sort of generate a shortcut for this access and at the same time evaluate that it's not null, right? So it's actually a valid shortcut to a valid value. Good fun, right? So Microsoft, like I said, was surprised to find that people kind of discovered this as an idea. Other languages, some other languages have a with keyword that does a similar thing, if you're familiar with that. Visual Basic, I believe, has one, right, for example. So in C#, basically, you can abuse this expression for that purpose. Right, and then on the basis of these features we've seen so far, we can now do more complicated things. In C#9, we had relational parameters here, right? So month, greater or equal to 7, maybe. And we can introduce alternatives, either this year or the other year. And these, these logical operators are supported as well between expressions. So I can combine them there and say, I have a variety of expressions that have to be evaluated in conjunction. And then finally, I've got an example down here, which is sort of the business object-based example that Microsoft likes to focus on. So we have here an order object called O, and we're matching it. And I've used several different syntax variations here just to make it clear how you can combine these things. So for example, here I have actually decorated the row of the match with the type name. That is, of course, quite useless, technically speaking, because I already know that the order object O has to be in order, right? So that's clear. But if you look at the match line individually, then you might not understand this immediately, right? Let's say, I mean, this could be several screenfuls of conditions, and all I see is the condition here that says there's a first value that is expected to be smaller than 0, and the second value I don't care about in that case, right? Underscore. But the order gives me an extra decoration in there. And in the same way, I'm also using the labels, item count and item price in there. They're also optional. They just tell me which fields are those that I'm mapping against, right? So these are just variations. The following lines basically perform the same matches. So in this case, we're saying I don't care about the item count, but I'm matching if the item price should be smaller than 0, for example. And I did not use the same labels and decoration there a second time because perhaps it's enough to do it once, right? So it's all about legibility, if you will. And then we have also got here the so-called guard clause, where I'm performing a calculation as an extra check, if you will. So we're extracting the two values for count and price, now just short C and P. And then we have a calculation that says if the total value in this case is pretty high, because we have so many items and they are worth so and so much, then we return another different result that says the order is quite valuable because there's a high value to it, right? So again, I can talk about this all day, but you've seen the example, I suppose. I hope it doesn't shock you too much. This is the kind of thing that Microsoft thinks we could be doing. I wouldn't say that I actually do this all that much myself. Sometimes it makes sense if you're implementing a test for business logic type rules or something like that, you know. Obviously, I suppose if you try to encode the same check in some sort of if-else based construct, then it would be a lot more verbose than this, right? On the other hand, a lot of people look at this and say to me, well, that looks horrible to me. I can't read this very well. I'm really not interested, right? So entirely up to you. But this is how those different features come together when you primarily think about business data structures. Okay, so that's C#9. In 10, we had then added the nested path support. Here's an example. So I can now basically dig into an object hierarchy, address.city. I have an interesting other example of that. Let me just quickly bring that up. I think somewhere I have another write-up. This is a different project, but I just kind of came across this when I used it at the time. So this is a code generator. And so I'm digging around in Roslyn-style C# code constructs, right? And at the time, I was kind of implementing my logic here sequentially. So I started at the top, you know, is this an invocation expression syntax? And then, okay, I should now find underneath the expression of a particular type, right? And then I should find an identifier in there and so on. So that was the natural way for me to develop this, because I kind of looked into the data and saw, oh, this is what I have, right? Interesting, so that's my next step and so on, right? And then eventually, it turned out that I can also encode it using a match expression like this one here. So you can recognize the elements from above. This is the same, right? But I don't need all the temporary variables like this IE thing in here. And I can use the path syntax that I was just showing you from C#10 at this point to kind of dig into levels of the hierarchy that are lower down. Right? But then again, I don't have to, so I'm also combining it with another element on this level, right? So there's all kinds of flexibility in there. And in actual fact, ReSharper can even convert these things for you. So if I'm going to bring back, hang on, it's a little difficult to type here. I think, let me see, there's a slightly unintuitive thing, merge into pattern, there it is. Hang on, is that the right thing though? Well, the funny thing is that ReSharper does not allow you to actually find a smart tag on the front here or whatever, you know, here maybe, anything like that. So you kind of have to hunt around for, is that the right thing? Let's try this. Yes, that is the right thing. Merge into pattern is the name of it. I must say that I did not remember right now from the top of my head that that was the name of it. But anyway, so it can basically auto-convert these expressions one into the other type, which is helpful if you're just trying to get to know them and you're not so familiar with them. Just keep in mind, like I was saying, I'm going to undo this, that you have to kind of hunt around for, it's on the double ampersand, right? That's where I actually find the smart tag that allows me to perform this conversion. I have no idea why. We should ask JetBrains. They're actually downstairs, I think. See if they have an explanation of that particular bit. But yeah, anyway, it's a helpful little feature, and it works fine in my experience if you come across it. In this case here, I tested that a few times to make sure that it was actually the correct thing. Right, so going back now to the samples, where were we? We were right here. The final bit that I've not shown you yet is C#11. Here it is. And in C#11, we got the matching of lists, right? So actually, let me just run this. We can see in the output, there's all the different variations are being tested here. Here we go. So I've got this numbers list up here that contains the numbers 1, 3, and 42. And then I've just illustrated all the different matches down here to make it obvious which ones are the ones that match and which don't match, right? So we can match 1, 3, 42 with 1, 3, 42. Unsurprisingly, that says we have a match, right? Lovely. The rest of them is more informative. So if I leave the 42 out, that's not a match anymore, right? Can't do. If I add a placeholder, like in the third row down, then I have a match again. That's this one right here, yeah? So this one says true because I have a placeholder there. If I add another placeholder, we're back to false. So the number of elements must be correct, actually, for the match. I can, however, use the spread operator to say there could be multiple elements here, where the spread, of course, can also have 0 elements, right? Just to be clear, that's important to remember if you use it. And then, interestingly, I can also combine this with other types of matches. So if my first 2 elements are 1 and 3, and the third element is greater than 10, for example, then that is a match. Greater than 100, not a match, right? Because we know the value is actually 42. So this is how you can combine all this stuff. And then eventually, let me see, we have, hang on, down at the bottom of my various samples here, a couple of other combinations. I'm splitting my list here now. This is something we haven't seen yet. So the fact that I'm matching a list is obvious by the brackets, right? That's what indicates we have a list. Now we have 2 parts to this list, and the first part is extracted with the var keyword. I don't think I've pointed it out, but we saw it a couple times before. So that just extracts one value, var x. And then if I use the spread operator in combination with the var keyword, then it extracts the rest of whatever comes there, right? Which is, of course, a split into a head and a tail, as you would do for a linked list, basically. One item and all the remaining items. This is quite important for functional programming because people there tend to do that all the time, splitting lists up like this and processing the head and the tail elements individually. I believe there is also an example down here. Yes, there is. That implements one of these logic algorithms that functional programming often uses. So for example, if I was going to sum up all the values in my list of values, then I would first match the list that I receive against an empty list, in which case the sum, of course, is 0, right? That's for sure. Or if there is something in the list, I would split it into head and tail, like I told you above, and then I can calculate the sum as the value plus the sum of all the remaining values, right? Very simple, recursive kind of implementation. Of course, we know that in C#, this may give us problems due to stack overflows and all sorts. So I'm not generally saying you should now always do it this way, but as I was explaining in the beginning, it can be important to try to implement certain algorithms along exactly the same lines that you would in a functional language as well, right? So, final bit that you may have noticed here is that I'm using the span of int as my data type, which is interesting. And that's because when Microsoft first provided this functionality, people quickly told them that it was horrendously slow when used with the standard data types that you imagine, like a list of int or even an IEnumerable of int or whatever. The IEnumerable, by the way, is not supported by pattern matching in the first place. You could implement your own head and tail sort of logic on the basis of IEnumerable, of course, but that kind of defeats the purpose, right? So Microsoft ended up adding the support for the span thing to this matching stuff. Basically, you know, span of t, right? That's been around in .NET now for a while and is used in a lot of performance optimization scenarios because it basically guarantees that the data that is in the span occupies a consecutive memory allocation, right? So that makes it fast, and that also means that they can use optimized mechanisms to provide, for example, a split like this into a head and a tail part. There are also downsides to span of t because it can't do some things. It cannot be nested like a span of t or something, for example. That's not possible, unfortunately. So there are things or situations where this doesn't work. But in a case like this here, it's actually very useful. And since they have added type conversion support, I can simply pass in a list of int or an array of int or whatever I have really that works with the span of int. So in a case like this, that's exactly the data type that you should try to receive, because it means that you can then be passed in whatever type of list of values you want, and they will all be handled performantly with this matching mechanism. Okay. Right, so that's through C#11 basically where we stand at that point in time. Now, that was mainly the feature overview. Now, as I said, I have some interesting cases that are kind of like a slightly different syntax or whatever that you might not have expected. And I think the first one is one that I sort of stumbled over when I first looked at all this stuff, because I kind of read the instructions and I played around a bit, and then I saw an example where all of a sudden we match two values by putting them in parens right there. And I thought, oh, that's cool, right? So I didn't know this because the docs don't say, but apparently the switch expression also has support for matching multiple values that I put in parens. Well, it turns out that might be true from a usability perspective, but that's not true at all from a technical point of view, because what actually happens is that the syntax in parens simply instantiates an ad hoc tuple of multiple values. And once that exists, I then use the tuple matching syntax, the positional pattern syntax, that I already showed you to do it, right? So like I said, this is when I first looked at it, I found that quite confusing. I thought, hey, why did they leave this out everywhere? Well, because they didn't think it needed explaining or something, which I think it kind of does, because you might end up using it. It's a good feature to have, only it technically works differently and it's independent of pattern matching, really. And for that reason, they didn't think it was worth pointing out. So I'm pointing it out right now. So this is actually very useful in many cases. And I've got a couple of other interesting examples of using this in a little while as well. Oh, here's one actually interesting. I forgot I added this slide. Well, that's good. Another ad hoc tuple example. So I used this book, F# for Scientists by John Harrop. He's got a number of F# based algorithms in there that I kind of had fun porting for a while for various purposes. And he has this matching pattern like we see down there. So we basically match two values at the same time, right? I'm not going to talk about what this algorithm does. That's kind of my point in this regard, that we don't know what it does. But in F# we have the ability to actually match multiple values like this. And so that's what I'm also going to do in C#. And I can now match multiple conditions here, you see. So I'm assigning two values there to temporary variables inside the tuple, if you will. And then these are logical values, right? They are comparisons. They are either true or false. And then I can combine these different conditions right there and see which combination is currently true. Either the first one's true, the second one's false, or the first one's false, the second one is true. Clearly, if I was going to try to implement this with an ordinary kind of if-else construct, then either I would have to repeat myself a few times, or I would have to separately assign some variables, ahead of time, and then perhaps use an if-else to kind of construct the same thing there, right? So it would be both more complicated and also a lot more verbose. So that's a very interesting use, I think, of this matching multiple values at the same time approach. Right, completely different topic. These are technically all kind of different because they're just interesting side cases, really. We have just not seen that you can also have matches that use generic types. So in this example here, which is kind of interesting, you see that I'm matching on the variable e, which is, hang on, let me point this out to you. This is, oops, what happened? There it is, e, right? That's what I'm matching on, and e is simply an either. That is actually just the type. It doesn't even have a generic type, right? But in reality, I know that the either variable I receive could be of multiple derived types. There is a type right of t, and there is a type left of t. If anyone's firm with functional languages, you might totally understand what that is, but I don't want to go there right now, okay? So there are just two derived types, and they both have generic parameters, whereas my base class type does not. And the pattern matching syntax, that's really my whole point here, enables you to actually model this, right? So in this case, I have two generic parameters that I get passed in here into my function, R and L. Actually, there's a third one, but we're not using that. And I can now match those side by side by using the right of R or left of L expressions. I don't know what I'm doing here, you know, that suddenly makes everything vanish. There it is. Left of L, right? So that's kind of my point. The expressions that we use in a pattern match do not have to be sort of logically complicit, right? They don't have to fit together in some obvious way. Often they do, and typically it is also regarded a good practice to try to create matches that cover everything. However, this kind of pattern is also implemented here because I have a fallback, right? If I have a fallback, then technically I cover everything. Of course, in a case like this, you could imagine, you know, that there are a lot of potential fringe conditions that I'm not specifically covering, right? So that's up to the algorithmic implementation. And whether or not you think that's a great idea or very readable or whatever, it kind of depends on what you're doing right there. So in a case like this, that works perfectly. And as I said, I'd just like to kind of point out that the technical implementation of patterns does not require you to be, I don't know, more kind of complete than this or handle all cases or anything along these lines, right? So we're sort of just picking out two specific cases here. It could be a right of R, it could be a left of L, and everything else we declare as being invalid for our purposes, right? That's the idea. Right, so yeah, some people enjoy using switch matches now with patterns in place of a ternary expression, right? Ternary expression, question mark, colon kind of thing. Some people hate it, right? Think it's also not formatted nicely sometimes because it can be kind of long runaway lines if you have like nested ternaries or that kind of thing. So even in a simple case like this here, you could decide to simply use a pattern match in a place where a ternary expression would also do the job, right? That would be the same thing here. The pattern match is perhaps more sort of extensible if you find that you have to add other matches to it over time, which is possible here because I'm back to my either thing right there. Yeah, we already know that there are other cases there. In this case, I don't care, right? But it could be that I'm going to extend this in the future. But other people just prefer it because they find it more legible. So that's interesting. Right, so, I was going to point out here, there's a comment down here that actually says, in this case here, the variable L also receives the type of the match, right? Originally my E was either, and now my L is a left of T, so that I can dereference L.value, which is kind of cool, right? It does this automatically. However, if I use a different variation of the same syntax, like in this case here, I'm simply testing my result to see if there's a property in it that's called isSum, and its value is true, and then, you know, maybe just for fun, I'm going to call it sum, and also use it in the expression afterwards. This is all completely valid. However, the sum variable in this particular case actually holds the same type as the result variable that I started out with. So, I mean, if you think about it, that's kind of logical, because what other type would that possibly be, right? All I'm doing is testing for the existence of a property by using this property pattern here, is sum is true. There's nothing else. C# does not magically construct some extra type for me that only includes that one property or something like that, right? I'm saying that because I've had that discussion. People thought that might happen, right? But no, that does not happen. So in some cases, the syntax we're looking at here changes the type of the variable that I have available for further processing. In some other cases, it does not, where of course the end result, that is always important, is in fact the same, right? So if I'm testing the is_sum property, then the sum variable would also still have the is_sum property. And that's kind of the same as it was with the left of t, where I'm accessing the value that's in the left of t. So in both cases, I end up being able to access the values from this object, and that's cool. Right, let's watch the time before we only have an hour here, so yeah, all right, we're doing good. Right, so this is an interesting one here, I thought. I think it's one of the last ones of these simple examples. You know, in some languages, we have this funny operator, like in PHP, C++. Sometimes it's called the spaceship operator, that basically says, take two values, compare them. If one of them is bigger than the other, let's say A is bigger than B, then we return a positive result. If A is smaller than B, we return a negative result. If they're equal, we return 0. You've ever come across this semantics, right? Very common in comparison algorithm implementations, sort algorithms maybe, that sort of thing. And some languages had an extra operator for this, which is good fun. Now we have this behavior, for instance, in the comparer of t in .NET. And it always used to be kind of difficult syntactically to deal with those results, because you had to like put them in a variable and then go, you know, if smaller than 0, else, if larger than 0, else, right, like that. Well, now we don't, because we can use the relational operators to just match them and have all the cases combined in one syntactic construct. So I thought that's kind of cool as a use case, old-fashioned use case with newfangled syntax, right? Nice one, I thought. Okay, yeah, another example that I was just going to bring up quickly in some libraries, and I'm mentioning here the implementation of akka.net. The existence of patterns has actually changed the way that some things are done by default. So back in the day when we didn't have good pattern matching, they recommended implementations like you see on the left there, where we basically use generic methods like this receive of t to say these are the types that we're trying to work with and so on, right? And now they have changed after a while their guidance. This is already a few years ago again now, but they changed their guidance back then to say, well, we don't really need all these generic function calls anymore, because we can now very simply test which type of message we actually receive, right? Akka still supports both, by the way, right? So this is just that they kind of changed the default guidance to say we actually recommend doing this a different way now because of the new technical features that we have. Okay, so, and yeah, this is like the last of these introduction things before I get to the real functional stuff. So this summarizes just a few points. I already made some of them. In many functional languages, and I'm mentioning Haskell again because that was one of the ones I was confronted with, the use of pattern matching is very deeply embedded. It happens all the time. It is syntactically embedded in the language. I'm going to show you a couple quick examples in a moment. And so for that reason, we have to use different implementations. If we need to recreate those in C#, it's useful to know how that works exactly. The item at the bottom there explains the thing about looping, right? Since I had this recursive sum implementation and that sort of thing, right? In many functional languages, we don't have loops. Those of you who've never used one might find that very strange, right? But it's true, we don't have loops, instead we have recursion. And so these people did not, for some reason, decide to do this all a funny way. They just used the approach that is natural in their language. And for that reason, unfortunately, or not, we just have to understand how to use the same techniques in C# if we'd like to have this easy porting approach that I was getting at. Okay, let's see. So I've got a couple of simple things here to show you. First, somewhere in my sample solution here, there are a couple of syntax examples, very simple ones, just to kind of illustrate how other languages embed pattern matching. This is an example in Erlang. This is actually old-fangled Erlang that I used to program at some point in far history. But you can see the same today in like Elixir and things like that, right? Any Elixir people here? No? Okay. So they still do that, basically. These languages have built-in message passing constructs. As you can see by this receive keyword there, it's like nice and bold because it's a keyword in Erlang. And then messages are simply dynamic data structures, and they are received and processed using pattern matching. So in this case here, we see that we have a type of the message, which is called an atom, and this thing is basically a name, right? It says this message is of type add, and if it's of type add, it should also come with at least 2 values on it, which we're extracting. And of course in Erlang, as you surely know, right? No? All variables are in capital letters, right? Isn't that like the weirdest thing ever? Well, from today's perspective it is. They must have thought it made sense. But yeah, that's how it works. So these are variables. We're extracting them and then processing them. Just one example. The other ones are Haskell that I have here. So in Haskell, we basically use patterns to implement function overloads, which is interesting. In C#, we function overload by the signature, right? So we have variable types and they come in and that's my method signature and then I can overload it. But in Haskell, we use patterns instead. So if we would like to have a method that compares various types of food here, for example, we can simply say that the ones that are where both parameters are in fact equal, like in pasta, pasta, or pizza, pizza, or chips, chips, they're all true, as in these are equal, right? Everything else is false. And that might be a rather strange way from our perspective, but nevertheless a useful way in Haskell to implement certain algorithms right there, using pattern matching. And here's another one. We have a factorial implementation. So this one down here is actually uses the same logic I just told you about. So it says, if the value I'm getting passed in is 0, then we just return 1. That's one of my function overloads. If the factorial's input is 1, then the result is still 1. And if the factorial's input is anything else, whoops, so this is basically by order of evaluation, right? So we receive this x value. In that case, we recursively actually calculate the factorial, right? So that's how that works. Interestingly, there is a different syntax, so you can also do it like this here. With conditions and stuff like that. And what I always thought is fantastic is that Haskell has a keyword called otherwise, right? I like that. We should have that too. Otherwise is somehow a cool keyword, I think. Much nicer than else. A lot longer too. I don't know, I'm just saying. Otherwise sounds good to me. All right. And of course, finally, in F#, we even have integrated regular expressions, I'm saying. Why do I say that? Patterns, right? In F#, even though that is, as we know, a .NET language, right? So that's exactly what you can use on .NET if you like. And we can do pattern matches here with the match keyword like this, which is almost exactly what I showed you with the sum earlier. But we can also use this other syntax here, where you might notice a couple of pretty confusing things right away. Number one, there is no match keyword anymore, so we somehow have to divine that that's a match anyway, right? Well, it kind of looks like one, so that's not so hard. But here's the prize question. What are we actually matching on, right? Because there's no variable, right? It's gone. We don't need a variable anymore, suddenly, in this particular syntax, because the variable is simply implied to be the value that we're matching against. And we actually have syntactically no way to refer to it even if we wanted to, right? So that's just not possible. So if I do want to refer to anything, as I do in the case here of the x's, right? That's the typical functional kind of thing. We have one x, we have multiple x's, right? So the x's are like the tail part of my list. And if I want to refer to something at all, then I need to extract it from my pattern. There's nothing else, which is also kind of exactly the way functional languages like to work, right? Make everything that you actually need to work with, that you need to refer to, very explicit. Okay, so that's kind of a philosophical approach almost that they have encoded here. This is a part of F# that was created on the basis of syntax from the ML language. That is a much older kind of functional language that F# used as a template for its own syntax. So they didn't make that up, but they ported it from elsewhere. Okay, so that's this stuff. Now, in this C#11 example here, I have a couple of other, this is the first one here, a couple of other sample ports that I created. So we have here, as an example, some existing F# implementations. This is kind of similar to what I just showed you. It uses this function keyword, and we're then matching an empty list that gives us an empty list, fair enough. And we can also have like the first element, which we call H1 for head 1. And then the second element is H2 for head 2. And then T is my tail element, right? So you see that somehow F# still manages to make the syntax somehow more concise than in C#, right? That's in C#, it's a bit unfortunate, actually, the way they chose to do it, because in C# we've seen that if I need to extract a value from a pattern, I need the var keyword, right? We saw that multiple times, which is fine if you think about it, because in C#, of course, variables are typically modifiable by default. So we need to mark those variables that are not supposed to be part of the match with a keyword to say those are the ones we're extracting. Now, the thing that they didn't quite get right in my eyes, though, is that if you ever want to use a variable as part of a match without extracting anything, in fact, you can't use the variable or any normal variable for it, but it has to be specifically a const value that allows you to do that. Right, so they introduced two requirements where one would have been enough, right? So in F#, variables are not ordinarily modifiable. So if I'm simply matching here, you know, I just mention by name, let's put it this way, this value called T, then I know that that's an extraction, because there isn't any other T in scope that I could be matching against or anything, so I'm extracting something, right? It's that simple. They don't need any particular markup for it. And in C#, they basically introduced two requirements. So if I wanted to match against an outer existing T, then I would have to make that a const T. And if I want to extract, then it needs to be a var T. And that means that in both cases, my syntax is more verbose, right, basically. So that's a little unfortunate, really, that they chose to go both ways. I guess it's just an example of the fact that in C#, all of this syntactic stuff is still somehow an import from elsewhere, right? They never kind of think along the same philosophical lines of keeping the syntax really concise and so on. But anyway, this is what we get now if I do the same thing in C#. So here we go. That's my extraction of the two head elements and the tail parts, which is kind of cool, right? I mean, it's a bit longer, whatever. It's readable enough. It's easy to create, no problem. So I think that's great. Now, the construction, of course, is not quite so great. I mean, basically, we have here the C# variation that simply uses this operator of the double colon here. Whoops, I can't highlight this. There we go. This operator is the equivalent, of course, of the extraction operator, which kind of makes a lot of sense, and it can concatenate the data again on the other side. And in C# I can't really do that, right? So I'm going to have to use here a list in this case, and I'm going to have to use a concat there to bring it back together and so on, and already my syntax, of course, goes a lot more verbose. And I've got another example here where you can see that even more clearly. This function uses another interesting looking match here that I can model in C# like this. And focusing on the C# syntax, you can actually see a little more clearly what that is. It's a list that contains lists again, so nested lists, right? We can also see that, of course, by the parameter type up here, which is actually list of int, right? So like that. So we're matching the list as a whole. We don't really care what else comes after it, but we do want to know that there is something there. And we then kind of match this is the first part. Let me highlight that particular bit right here. So this basically says there must be at least the one item in the list right there. Yeah, that's what that says. Anyway, just comparing, this is perfectly fine. So I started out with this thing in F#. Actually, it kind of ends here. Right? That's all I need. And I end up with this in C#, and that's impressive, right? So the matching is almost the same, basically. Now, however, in F#, I end up using this one line here of code to create my return result. And in actual fact, this is already longer than it would be in many functional languages, because F# now has a rule that says we can't easily import namespaces like the namespace list anymore. So if I didn't have to repeat list dot all the time, then it would just be map, head, and so on, right? So it would be half the length, basically, right? So that's the only requirement in F#. And in C#, unfortunately, the same logic is like this, right? So that's because I'm using list of int. I can't actually even use a span because they can't be nested, right? Like I mentioned early on. And then I'm kind of stuck by using link expressions to kind of make that shorter. I even went through a couple of different iterations of this to see if there was some way of making it significantly shorter, but there isn't. Not like this. However, what we can do, of course, and for porting purposes that can make sense, I can simply create myself a few helpers. Right? So I created a few matching helpers, construction helpers, and then all of a sudden the result is this. That's the same thing that F# does. And that's a lot more impressive, isn't it? It's even shorter, I think, than the F# version, right? And hey, we're not counting bytes. All I'm talking about is expressiveness and the ability of myself as the person who works on the port to look at this next to the F# and see, am I doing this right? Yeah? Do I apply these functions in the correct order like the original version also did, and so on? That's what I have in mind when I look at these. And of course, you know, this is a lot easier in this case here than it would be with this one, because this one doesn't really tell me anything, right? That's complicated to read and to understand, and that's exactly the type of code I'm trying to avoid when I'm porting these kinds of functional algorithms. Right, so, okay, now we don't have all that much time. I've got my final example to show you, and that's not a problem, we'll manage. This is it, right? That's good fun, isn't it? I was implementing, as I said, these functional data type algorithms. This is from a so-called red-black set, I believe is what it's called in the original. You know, red-black trees, right? They're like data structures, and when they kind of get out of shape, they can be switched around a bit with red nodes and black nodes, and yeah, never mind. I didn't exactly know how that worked from the top of my head either, so I found somebody who'd already done it, right? In an immutable data structure in Haskell, and then I found this function which is called balance in there, and this is it, right? And you look at it and you think, hey, that's kind of cool. I have no idea what's going on there, but it's kind of cool, right? So what does this possibly mean? And back when I first created my own implementation for this book, like I said years ago, hang on, we don't need this one anymore now. We need a different window here. Where are we? Hey, come on now, this one. All right. I ended up with this implementation, right? So that's what I created in C# back then. Yeah, that's pretty much it. It fits on one screen here, more or less. I mean, if it's formatted like this, I think if I format it differently, it kind of ends up being 10 pages long or something like that. And it's the same, trust me, right? But of course, you know, who would know? It's completely impossible. You can sort of understand the mapping, right? So if I look up here at the Haskell expression, it says that on the outside we're starting with a B, a black value, and that's what I have here, if my outer value is black, okay? And then we kind of have not left is empty, and left node color red, and that's what we have here. So we have a tree element nested underneath that is non-empty, right? And that's a red tree element. And from there on, we kind of dig further into the structure of the tree to see what's happening. And then, of course, the author cleverly constructed it so that the return expression is always the same, right? So we don't actually have to have any variations there. He just did it all by way of the extraction. Yeah, so I was then curious to see if there was a way we could possibly make that work in C# in a similar way. And it turns out that we can. Let me try to create some part of that for you here. Where are we? I do need a note for this, otherwise it's going to go wrong. So, oh, hang on. I wanted to do one thing quickly. I've got here somewhere some tests, right? .NET tests. These are for the library implementation here. So we see there's like 514 tests. They will pass, right? We're happy with that. Now, if I'm going to fiddle with this, now I'm in the wrong window though, suddenly. Hang on, let's just close these. I think that makes that easier. And then go back to Rider. Oh, come on now. Still doesn't want to do it. Where's my Rider gone? I mean, honestly. I think
you moved to a different desktop, right?
Yeah, I kind of think I did too, but I don't understand where it's gone now. I'm suddenly riderless. Now Rider is literally gone. Okay, hang on. That's not intentional, but we can fix that quickly enough, I think. I must have accidentally now closed it or something. Here we go. Okay. Now we're in full screen view. Where is this? Oh, there it is. Okay. Well, sorry about that. I don't know why that happened. So let's remove most of all this stuff here because we're not needing it. Now, since I explained the importance of these construction helpers earlier, I'm going to create myself a couple helpers here. So we have a const color R, which is color.red, right? And we have a const color B, which is color.black. That's what I also said. We're using those for matching, so I need to make sure, oh no, not that they are const values. And now I'm going to create a construction helper. I'll call it TT, and this gets a color C, a red, black tree of T for the left branch, a T question mark value, that is of the type T, of course, and a red, black tree of T for the right branch. And then nice C# syntax, we can simply go C, L, V, R, construct the whole thing, right? And with the help of this little construction helper, I can now code up the same kind of pattern. I don't know if we can keep this in view, maybe like this a bit. So I can simply say return the result of a match. So I'm going to match on node color, left value, and right, like this, and do a switch, right, like so. And then I can simply go and match. And we're starting with the B right up here, the outer black value, and then just match what comes inside, right? So we've got a new tree with an R, and another new tree with an R, and then we extract A, var X, and var B from there. See, I'm here, right? So this is the bit that I've now encoded there successfully. That's kind of the same in C# now. And then I must make sure that I'm on the correct level, so I'm kind of getting out of this level. And then we have var Y and var C, closing paren, var z, var d, right, like this. And then we can construct that again with the TT expression and go TTR, TTB, A, X, B, and Y, and TT, B, C, Z, and D, like that, right? Okay, well, cool. So now we have one row. Now all I'd have to do is code up all the rest, and then we can see what happens. Let me just quickly jump back here. So while I've got this broken, of course, we should see that there's a build error even or something like that, right? Just to be clear, we're in the right demo here, so that was on purpose. And now I'm just going to pull in, because we don't have much time, and watching me type this is not that exciting anyway, is it? So I'm just going to pull in this entire return construct here that is now complete and follows the same logic as before. And that is my C# syntax. Let's see what my test says. It succeeds again, right? So that is my C# syntax now that models the exact same thing as my Haskell construct up above. And, you know, with the exception of differences in the specific syntax that we're using and everything, it is exactly the same, right? Which is cool. So now I know that if I made any mistake in there, which I have done many times when I did this, right? I would be able to see exactly, comparing the variables from the extraction and whatever, is the order correct and the levels are all correct and so on. All of a sudden, C# pattern matching is actually able to do that same thing right there. Microsoft doesn't tell you this in their documentation. I hope you enjoyed seeing that it works anyway. Of course, like I said, this is a bit of a crazy one for the end right there. So here you can get all the sources of everything I showed you today. If you're interested, the presentation itself is also at the QR code. Why I keep saying barcode to these things. And I think that's all I have. I'll be around in case you have questions. We're out of time. There is lunch now, I believe, so let's not be the last to get there. Thank you very much for being here. I appreciate it.